Right, so Frank, you've got 25 minutes, I think, so go ahead.
So thank you for the being able to give this talk, and welcome to day 2. I'm going to be starting the atmosphere discussion with an overview of atmosphere chemistry on Venus. Due to time constraints, there are a number of important and interesting topics I won't cover, such as electrochemistry, cloud chemistry, phosphine, cosmic rays, and the supercritical layer and the lowest scale heights. So this is a chemistry-centric view of Venus's atmosphere, but what we observe and need to understand is a much larger system whose components interact on a range of timescales. As an example of the interactions within Venus's atmosphere, production and loss of the unidentified UV absorbers is likely affected by chemical processes. And then inhomogeneities in its distribution, just like inhomogeneities in the distribution of mesospheric ozone on the Earth, produce localized differences in albedo, which induce localized variations in heating, which in turn drives circulation patterns that affect the distribution of chemical species. So as I go through my talk, I'll try to point out some of these linkages, but there are others we'll hear about over the rest of today and tomorrow. Okay, if you're online, can you please mute your mic? Thank you. So since this is the first atmosphere talk, let me start with a quick review of the atmosphere's general structure. The portion we're considering at this conference extends generally from the surface, about 90 bar pressure, to about 110 kilometers, about 1 microbar. And what I'm considering as the troposphere extends from the surface up to about 60 kilometers, with the mesosphere and thermosphere above that. The global cloud layers extend from about 48 kilometers to 70 kilometers. Photochemistry, which is the chemistry that's driven by absorption of solar photons, dominates in the mesosphere and thermosphere. Chemistry in the troposphere is affected by the elevated temperatures there, but based on work by Bruce Fegley's group, thermochemical equilibrium may only be reached in the lowest kilometer. And then the lowest 12 kilometers is where Levenwat and Schubert have proposed the atmosphere behaves like a supercritical fluid. The temperature profile below the clouds appears to be close to adiabatic. And then within the cloud layers, there are stable and unstable layers. And above the clouds, temperature profiles vary with latitude and local time. So global scale circulation has 3 distinct patterns that are relevant, particularly for the chemistry. There's a relatively slow meridional circulation similar to the Hadley cell on the Earth, but observationally it extends up to about 60 degrees north and south. And then the westward zonal superrotation dominates the cloud region and mesosphere. And at the highest altitudes, the subsolar and anisolar circulation is important and affects the distribution of species like carbon monoxide in the mesosphere. So moving now into the chemistry realm, our observational information comes from measurements and upper limits on these species. I don't think I've omitted anything that we've actually detected or have an upper limit on, but let me know if I've missed something. The species that are in red are ones I'm going to be talking about in this talk. And gaseous H2SO4 appears in both columns because we have detections of it in the cloud layers and lower atmosphere, but we have an upper limit on it which is important for the chemistry processes in the upper mesosphere. O2 is in both columns because we have detection of the strong air glow emission in the Singlet delta band, but we don't have an abundance or detection of its ground state abundance. So for this talk, I've divided the chemistry into carbon-based chemistry and sulfur-based chemistry, and then the oxygen chemistry. Oxygen is basically common to both of those, so it's interplaying with both of those. And you'll see small red boxes up in the upper left, mostly in the upper right. Upper right on your screen. Those are not Marty's thoughts, for those of you who were here yesterday. There are some of the key ideas I want to convey. And the animation on the right on this slide shows the process of how transport interacts with chemistry that's shown over on the left. So carbon monoxide and oxygen produced from photolysis of CO2 on the day side is transported at high altitudes by the subsolar and antisolar circulation to the night side. And then the atomic oxygen there combines to form molecular oxygen. Not shown in this animation, but also important, is that the same process of forming molecular oxygen occurs on the day side. And we have an observation of the air glow emission on the day side that corroborates that. So the left side of this shows the observations and models of carbon monoxide in the troposphere. The top is the vertical distribution and vertical profile. Bottom is the latitudinal profile. And you'll notice on the latitudinal profile that it basically increases from the equator to about 60 degrees north and south, and then starts to decrease above that, beyond at higher latitudes. So the right side is a conceptual view of capturing what's in those observations and trying to tie that then into the transport. So you have the Hadley cell circulation through the troposphere going from the equator up to 60 degrees, which then leads to that increase in carbon monoxide along with, and then in the polar region, that then falls off. And you also have what's observed observationally is that the carbon monoxide in the troposphere on the dawn side of the night is less than what it is at the dusk, which conceptually could be due to CO production on the day side. Question is what the mechanism is for that. And so some of the unresolved issues that are actually portrayed in this picture are that the carbon monoxide production coming out of OCS, which would be a tropospheric source of carbon monoxide, is smaller than the observed gradient in the carbon monoxide profile. And what's described here is that the older concept that carbon dioxide is photolyzing at the cloud tops to produce carbon monoxide. But what we'll see later is that carbon dioxide photolysis is actually occurring much higher. So this connection to carbon monoxide potentially downwelling at 60 degrees north and south is actually a connection up to probably 85, 90 kilometers altitude, because that's where the carbon monoxide is being produced out of carbon dioxide photolysis. This is now looking at the carbon monoxide observations, a partial subset of them in the mesosphere. On the left is shown the SWAR observations in the upper mesosphere at the terminators from about 84 kilometers up to 140. And you can see that there's different behavior at dusk versus dawn at the lower altitudes compared to the higher altitudes. There's also different behavior for the profiles at the equator versus the poles versus mid latitudes. And what's shown on the right are a couple snapshots from observations with submillimeter of carbon monoxide at 105 kilometers. These are relative to, the colors show the amount of carbon monoxide relative to the carbon monoxide at disk center. So red means that in that circle, which is a beam location, the carbon monoxide is larger than it was at disk center. Blue means that the carbon monoxide in that beam was smaller than at disk center. And so you can see the spatial patterns change over the 2-year time period between these. In August 2007, there's much more a asymmetric view at 105 kilometers compared to the much more symmetric fall off relative to disk center in 2009. So again, the mesosphere for carbon monoxide is showing that it depends on altitude, what the behavior is, and there are significant time variability in it. Much more variability than we observe in the troposphere. The other side of the carbon dioxide cycle is what happens to the oxygen. And what you see on the left is a spectrum showing the absorption by O2 in the Earth's atmosphere, which are the 3 lines, O16, O17, and O18, and the absence of an oxygen line at the position where it would be for Venus. So there have been 3 observations over 23 years trying to detect molecular oxygen via spectroscopy. None of them have succeeded. And the lowest upper limit was the observation in 1982, various interpretations on that. Part of the issue in interpreting that is that the way it's described in the published paper is it's above the quote visible cloud top, unquote. Well, actually, if you try to run numerical simulations of the radiative transfer, because there are no absorbers, no strong absorbers at 760 nanometers, this radiation is actually sensitive all the way down to like 50 kilometers. And what we'll get to late, when I say I'm discounting their detection by the PV mass spectrometer, that's why. If you had the reported amount of O2 at the time of certainly the 1982 observation, probably the 1972, maybe not the 1995, I'm not sure if I was sensitive enough to that, you would have seen that amount of O2 show up in these remote spectroscopy. So and there are other reasons to discount that Pioneer Venus detection. So. Okay, so what's the overall chemistry there? We know the destruction side of CO2 is relatively simple. That's just photolysis of CO2. Production side is much more complicated. Direct recombination, CO plus O, is very slow. The Mars cycle, which involves hydrogen and OH as a catalyst, works okay for Mars, where the level of depletion of O2 compared to CO is much smaller, but it's too slow for Venus. And for Venus, what we find is much more efficient and is needed is chlorine catalyzed chemistry. The cycles that are shown on the right have been confirmed by laboratory study. There's another one down in the bottom left, which has not yet been confirmed by laboratory study. In numerical models, that's contributing about 20% of the total. 80% is coming through what's shown on the right. And now, how do these results compare? The results out of models compare with the observations? Well, the one I'll highlight there initially is the pair here from Pernice et al. 2004, where you'll notice this run was done with no chlorine catalytic chemistry. This run was done with the chlorine catalytic chemistry. The chlorine catalytic chemistry decreases the column O2 abundance by over a factor of 10. So it is extraordinarily efficient, and it's necessary to come even close to the observations. If you run with nominal chemistry in the mesosphere, both the modeling that I've done, which is Mills and Allen 2007, and the modeling that Vladimir Krasnopolsky has done from his 2012 model, come up basically the same as far as the O2 column abundance. And what I'm doing here is, for simplicity, assuming this, characterizing things in terms of the partial column above 58 kilometers. And by comparison to the observation, by that measure, it's the upper limit translates to about 0.8 by 10 to the 18. And so the nominal is about a factor of 10 higher than that. And the two that are highlighted here in green, I'm going to discuss further on the next slide. So these two models, one was a publication I did in 2006, the other's from Rimmer et al. 2021. What we did in the 2006 publication was to hypothesize a reaction occurring in heterogeneous phase on aerosols, where you have CO plus O. And we found we could get down to a column abundance that was about 2.6 by 10 to the 18. If we assumed that rate was about 10 to the minus 5. Well, the obvious question is, well, what if you make that rate faster? What happens? I didn't do that simulation with aerosols, but I did do it in a more general way with gas abundances, which is the plot shown down on the bottom left. And what I'm manipulating there is the stability of ClCO, which is a critical intermediate in this process of oxidizing CO back to CO2. If you use the nominal value for that, you get the solid line profile for carbon monoxide. As you increase that thermal stability and thereby increase the rate of production of CO2, the carbon monoxide shifts over to the left, becomes distorted compared to the observations, which are the other curves. That's a general result. So if you simply drive the CO plus O reaction faster, yes, it can bring the O2 abundance into agreement, but it distorts the carbon monoxide. No way around that. Rimmer et al. Did something quite a bit different, well, significantly different, in that what they did was to increase the pH in the clouds and thereby allow it to pick up oxygen and sequester that in the clouds, but not sequester or do anything to the carbon monoxide. And what that did, which is shown by the yellow dash curve compared to their nominal, which is the black solid one, was to reduce the amount of oxygen going into the cloud layer or being available in gas phase, and thereby reduce the apparent column abundance. They claim, however, that they're only a factor of 2 to 3 above the upper limit. And because they're close, I mean, they've reduced enough the oxygen abundance in the multiply scattering upper cloud layer that that might be true. But if I compare that to the Traugott-Lenine upper limit that's shown there, in the mesosphere, they're a factor of 10 above that. So I'm not convinced that they're really as close as they claim to that observational limit. One of the critical things that this brings up then that goes into transport is what's the amount of mesosphere-troposphere exchange? How much carbon monoxide that's produced in the mesosphere has to be transported into the troposphere in order to be recombined to form carbon dioxide? That's an open question. So now I want to shift over toward the sulfur chemistry. And the first part of that I'm going to look at is the sulfur oxide chemistry. And it's important to note here that although I've got 2 separate boxes for atomic oxygen, molecular oxygen, one for the carbon dioxide cycle, one for the sulfur oxides, the chemistry doesn't care where that oxygen comes from. Doesn't matter if it comes from SO2 or CO2, it's still going to behave chemically the same. So there is an interaction between these 2 chemical cycles. Starting off with the observations for SO2. SO2 is the primary form in which sulfur exists in Venus's atmosphere. On the left at the bottom right, you'll see highlighted the data points we have summarized by the Virtus observations of SO2 in the lower atmosphere. Note that it's about 100 parts per million. By the time you get above the clouds, that's now down to a few tenths of a part per billion, and then minimum somewhere around 80 kilometers, and then it starts to increase again. And that increase in the upper mesosphere shows a lot of temporal variability as to the absolute amount. There are also puzzling differences, but depending on which instrument did the measurements. So the submillimeter observations are consistently different than the occultation instruments, SPICAV and SWAR. But they all show the same relative behavior, that SO2 increases with altitude above 80 kilometers. So I'm going to take that part as being observationally confirmed. The plot on the right is showing the SO2 as a function of latitude. Peak is occurring at the equator and then dropping off as you go toward the poles. So there's also temporal variability and spatial variability beyond this. And this is now looking at, on the left, the cloud top and in the UV. On the right is somewhere in the middle of the upper cloud on Venus based on TechSea's observations in the 10 to 12 micron window. And on the left, you'll see there's the episodic increase followed by a decline, another episodic increase followed by a decline. Okay. All right, I'm behind schedule. And on the right, the circled water up at the top, which is actually an HDO observation, shows a good anti-correlation with the SO2 observations in the upper cloud, which are shown down on the bottom right, but only on the longer timescales. If you look at this on the daily or shorter timescales, this correlation really gets washed out and disappears. Possibly that's because the water vapor is a factor of 100, factor of 10, factor of 100 more abundant than the SO2, and therefore variations in the SO2 on short time scales aren't large enough to affect the water. Okay, this is the chemistry that's shown here. Traditionally, for the sulfur oxidation cycle, the source of oxygen is considered, as we saw in that carbon monoxide profile concept view several slides ago, is considered to be from carbon dioxide. However, what you can see in the plot on the right is that the altitude range where sulfuric acid is being produced in models around 64 to 70 kilometers is really in the range where SO2 is dominating as the source for atomic oxygen. So this chemical process is occurring both for production of sulfuric acid above the clouds or within the upper cloud, and then links to the lower atmosphere because the destruction of sulfuric acid is then driven by condensation settling down to the lower atmosphere where the sulfuric acid evaporates and returns back to the gaseous form. And now comparing observations to models. One of the issues that I highlighted earlier from the observations as shown on the left with the purple boxes in the bottom right and top and center of it is this large decrease as you go through the clouds in the SO2 abundance. The Bierson and Zhang model was able to reproduce that only by going to either a very slow eddy diffusion and then supplement or by, having a very low abundance of SO2 in the lower atmosphere. Model on the right from Rimmer et al. 2021 reproduced the fact that they could get that decrease going through the cloud layers if they had very low SO2. They could also get it from on what the other case was, but the third case that they looked at was increase in cloud pH. And the decrease in eddy diffusion, while plausible, is in significant disagreement with observations of eddy diffusion. The decrease in SO2 in the lower atmosphere is also in conflict with observations. So the only thing that fully agrees with observations at this point is Rimmer's suggestion of increasing the cloud pH. As far as the upper mesosphere enhancement is concerned, one of the sources there is S8 as shown in the plot on the left. And that by having an S8 flux, they're able to bring that down into the model and have an increase in sulfur as they go down through it. The other part, and let's see. So the idea here is that with the primary SO2 reservoir being in the lower atmosphere, if you just had photochemical destruction, you'd have a monotonic decrease as you go upward in altitude. But because we have this inversion layer in the upper mesosphere, there has to be a mechanism for transporting that sulfur dioxide in some other form up to the upper mesosphere. As I was mentioning, the one on the right, they do that through polysulfur, S8, injected at the top. Models shown on the right that are nominal chemistry, which is the Mills and Allen and the Krasnopolsky. Neither of them reproduces that upper mesosphere inversion, but if you add sulfuric acid as a transport mechanism up there by prescribing the sulfuric acid profile, then you can get that upper mesosphere inversion. Is that plausible? Well, this does a comparison to the upper limit, which is shown by the red bar on the left, and for H2SO4 in the upper mesosphere. And it's certainly the S8 case that Bierson and Zhang have done is consistent with that. The models that use sulfuric acid possibly are consistent with that, but that would require some actual RT radio transfer modeling in order to go through and check it. And both models are leaving aside the actual mechanism of how you get the S8 or the H2SO4 up to those higher altitudes in the mesosphere in order to be present where they can decompose. So the other side of the sulfur chemistry, which I will quickly try to go through before Sebastian throws me off, is to look then at the reduced sulfur chemistry. And this is where you get into S2O, SO-dimer, and polysulfur. And what's observed in the mesosphere, what's observed in the lower atmosphere is shown here. What's interesting to note here is that even though this cycle should span both the mesosphere and the lower atmosphere, which would mean you'd be observing similar species in both places, the only one that's been observed in both places is OCS from this reduced sulfur. And one of the reasons that we're really interested in polysulfur and reduced sulfur cycle is it's been proposed and has spectral characteristics that match those of the unidentified UV blue absorption, along with ferric chloride, which I think somebody's going to be talking about later. So this is showing CO versus OCS. There's an anti-correlation in the troposphere. Left side are the vertical plots. CO increases with increasing altitude, OCS decreases with decreasing altitude, but quantitatively they don't match. Similarly for latitudinal profiles. And the chemistry there is summarized here in terms of what's been proposed. In keeping with the color scheme that I've been using, the ones that are highlighted in red are not confirmed by laboratory studies. The ones that are in orange, yellow here are partially confirmed by laboratory studies, but not completely. And there's a really important issue that I think is being glossed over in that circulation studies are using fits to the CO and OCS observations to say that they are getting the correct circulation in the lower atmosphere. But they're basing it on that using this chemistry, which was empirically fit to the same observations that are being used to compare the circulation studies. So there's quite ample room in there for getting a tautology or a truism that we're comparing things that are should be the same because we've defined it to be that way. So we have to be careful in how we do that. Key steps that are needed in order to get through this are producing S2. Once you've gotten to S2, there's really only one clear pathway to go from S2 up to S8 or S3 through S8, and that's just adding on sulfur. Though we don't have measurements of that, but it's a fairly clear process. How you get past that step of producing S2 has been the subject of several papers. What's shown on the left is from the schematic from Pinto et al. On the right is an alternative schematic from some older work I did. A newer paper from Menares et al., which is part of an ongoing dialogue in Nature Communications, suggests that the pathway that we propose going from SO-dimer back to S2 as a production pathway for S2 is not correct, but there are some questions about what was presented in that paper. And they also propose that it goes through S2O and through SCL. Unidentified absorber. And I'll skip that, and there's the summary. Okay. Yep.